Lesson 4. So this is the last part that's a review of grade 10. Everything else will be essentially new. We're just building off of what we are doing. We're going to do acceleration all through this unit. Everything deals with acceleration and non-uniform motion. But let's take a look at some velocity time graphs. Why are they so important? Well, if we were looking at a position time graph, so a position time graph, if we're having acceleration, so with acceleration, that gets a curve. Curves are terrible. Curves are hard to read. They're hard to get information from because they're so difficult. If we can make things a straight line, always easier. Well, that's what a velocity time graph does. It makes acceleration look like a straight line. If it's constant acceleration, it'll be a straight line. It's wonderful. Now, why is that? Well, it all depends on what the slope is. So if we always remember that it's the rise over the run, mathematically y2 minus y1 over x2 minus x1, as always. But let's make a specific case for velocity time graphs. y2 minus y1. So that's, like our final y minus our initial y, which, if we're looking at what our y values are, that's velocities. So we've got velocity final minus velocity initial, so our change in velocity. That's starting to look familiar here. Now let's look at what our x's would be. So x's is time. Time final minus time initial. Well, that sounds awful familiar, like time interval. That's our slope. Slope of velocity time graph is change in velocity over change in time, which we just said in the last lesson was acceleration. It's wonderful. Now there's a couple of big differences more information we can get from a velocity time graph and that you can't get from a position time graph, or it's just a lot harder. One of the things though that is important to make a difference between is related to the slope. Position time graph, it tells you what direction the object's moving. Velocity time graph, it does not. So for a velocity time graph, direction of motion is not connected to the slope at all. If you want to know what direction something is going, look at the graph. It's telling you the velocity. So if the velocity is 20 meters per second forward, it's moving forward. So it always tells you. So if the first point here, 1 second, it's maybe 12.5 meters per second forward. It's moving forward. That comes from the velocity, not from the slope. What is the slope? We just said it's the acceleration. So let's write that down one last time. It is the acceleration. From this plot, we can also see that the velocity is changing in. Changing in a positive direction. The velocity goes from 0 to 12.5 to 25 to 37.5 to 50. So it's changing in a positive direction. And the acceleration, well, that line, the slope of the line is positive. So the acceleration is also positive. Why is that important? Well, let's take a look at how we can figure out if things are speeding up, slowing down, at a constant velocity, or at rest. And it all comes down to the signs and directions of the velocity and the acceleration. If we're speeding up, the direction of the velocity and acceleration are in the same direction. This is exactly like this graph that we just looked at. Both are positive. Our velocity is positive numbers and our slope is positive. So that one, it is speeding up. So that can be both positive or both negative. If it's slowing down, well, it's going to be they're going to be opposite. If one's the same, the other's going to be opposite. So this one is the opposite directions. So if you have a positive velocity, you'd have a negatively sloped line. If you had a negative velocity, you'd have a positively sloped line. The other way to always know which way things are slowing down, just look at how the numbers are changing. If the object is going to a faster and faster speed, it's speeding up. If it's going to a slower and slower speed, closer to 0, it's going to be slowing down. How do we know if it's at a constant velocity? Well, if I was, after this 4-second mark, if I wanted to stay at 50 meters per second, that's my constant velocity. I have to make sure that my graph says that. So over time, my line would stay on 50 meters per second. So it would be, the slope is 0, so we get a horizontal line. If it's at rest, there's one point on this graph above that is at rest, and that is when it touches the x-axis. So our x-axis is time, so these are our x-intercepts. This one hits it only at the very first point. When the time is 0, the velocity is also 0. There's no other point on this line that is a velocity of 0. And you will only see those on the x-axis. So let's try this out. Let's look at some examples. We've got this graph. We are going to fill in this chart. We're going to do 2 together, and we'll do the other 2 in class. What we're doing is we are describing the velocity and acceleration, and then we're also going to calculate the acceleration. Let's work on describing things first. The velocity, we want to describe it. So, start with the first point, 0 to 5 seconds. It's starting from rest, so that's an important point. Start from rest. And then what's happening to the velocity? Well, it's speeding up. It's getting faster. So then we can say it's speeding up. And what direction is it moving in? We're in positive numbers on our velocity, and it does have a west direction here, so we are moving west. Amazing. Wonderful. We've described our velocity. Let's describe the acceleration. That looks like a pretty steep line to me. So we're changing pretty fast in terms of what direction it is. It's a positive slope line, so we are accelerating west as well. So we are accelerating west. And we can talk about how fast this acceleration is. We don't want to say fast because fast sounds like speed or velocity, but instead we can say it is very rapid. So we've got a very rapid acceleration, rapidly changing velocity. We've described it. Now we've got to calculate it. Calculate the slope. I'm going to use the equation. Let's do this. Change in velocity over change in time. We go from 0 to 25 meters per second west and 0 to 5 seconds. So our final velocity, 25 meters per second west minus 0 meters per second over 5 seconds minus 0 seconds. 25 minus 0, 25. 5 minus 5, 0, 5. 25 over 5, that gives us 5. And then we get 5 meters per second squared with our direction west. Huzzah! Calculated. Awesome. Let's work on the next one, 5 to 10 seconds. We want to describe the velocity. This time we're not starting from rest. We are starting at 25 meters per second west. So we are still moving west. What is we're doing though? We're going from 25, then we go down to 20, then we go down to 15. So we're slowing down. We're getting slower. So we're slowing down. No, nobody wants to go slower. But what direction is it going? Again, just look at if the velocities are positive. If they're positive, it's west. So we are moving west. Okay, we've described our velocity. Let's describe our acceleration. Now we have a negative slope line. Negative slope, negative slope, negative slope. Well, if positive slope was west, then negative slope is east. So with this time, we're accelerating east. So that's important. So if we're moving west and accelerating east, our directions are opposite, which means we're slowing down. So we're on the right track here. Everything is clicking and working together. It's hard to say if this is rapid or not rapid. It's kind of in between. So it's hard to describe in between, so we don't need to worry about it. Let's calculate. make sure we don't get confused here. This acceleration, same equation. Now let's make sure we get our right points. So in this one, our final is 15 meters per second west, initial 25 meters per second west. And we're talking about 10 seconds minus 5 seconds. 15 minus 25 minus 10 over 10 minus 5. So minus 10 over 5, we get minus 2 meters per second squared west. I've said this before and I'll say it again. If you can, we don't like negative answers. We'd rather change the direction so that it is positive. So this one becomes 2 meters per second squared east. And again, I want to emphasize that in 0 to 5 seconds, our acceleration is west and our velocity was west, so we're speeding up. In 5 to 10 seconds, our acceleration we just said is east and our velocities are west, so we're slowing down. But we're still moving west in both cases. It's really important to start looking at those details very, very carefully. Do 10 to 20 seconds and 20 to 25. Now 10 to 20 should be fairly quick, but do it anyway. And then do 10 to 20 to 25, and we'll take them up in class and we'll go over some more workbook problems.